Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read, recorded, and produced by JohnLothe. Chapter 12. Pitch. The velocity of sound. A particular object has some natural period of vibration, and in the case of simple harmonic motion at least, this period is proportional to the square root of the mass of the object divided by the restoring force. See equation 8-4 on page 107. In the case of the pendulum, where the restoring force is gravity, which increases with mass, the period varies as the square root of the length of the pendulum divided by the acceleration due to gravity. See equation 8-9, page 112. This means that we generally expect that of two similar objects, the larger and more massive will have the longer period of vibration. It will consequently produce fewer sound waves per unit time, and the individual waves will have a longer wavelength and a lower frequency. The period of vibration can also be varied by changing the size of the restoring force, the period shortening as the restoring force increases in size. A taut string is more difficult to pull out of its equilibrium position than a slack one is, and from that it is clear that the force tending to restore the string to position is increased as the string grows tauter. Of two strings, otherwise alike, the tauter snaps back faster, and, if it is a bowstring, shoots the arrow farther. That is why bowstrings are kept as taut as possible when the bow is in action. A taut string, snapping back quickly, naturally has a shorter period of vibration than a slack one has, and produces sound waves with higher frequency and shorter wavelength. From experience, however, we know that all the factors that serve to produce a sound wave of low frequency also produce a deep tone, while those that bring about a sound wave of high frequency also produce a shrill tone. Large objects with long periods of vibration produce deep tones, while smaller objects produce shrill ones. Compare the tolling of a church bell with the tinkling of a sleigh bell, the strum of the string on the bass viol with the shrillness of the string on the tenor violin. In the realm of life, compare the trumpeting of the elephant with the squeak of the mouse, the honk of the goose with the tweet of the canary. The voice of a man with his longer vocal cords is deeper than those of a woman and children with their shorter ones. An individual can vary the shrillness of the voice he produces by adjusting the tautness of his vocal cords, though he is not aware he is doing so. And the sound of a freely vibrating string can be made more shrill as it is made more taut. This property of shrillness, or depth in tone, is referred to as the pitch of the sound, and it is quite obvious that the ear differentiates the frequencies of sound waves as pitch. As frequency increases, a sound is heard as increasingly shrill. As frequency decreases, a sound is heard as increasingly deep. It is easy to determine the frequency of a sound wave. The vibrations of a tuning fork can actually be counted in several ways, including, to mention a simple method, having it mark itself by pinpoint on a moving scroll of paper and counting the waves produced in a unit time. In this way, frequency and pitch can be matched. For instance, a tuning fork or pitch pipe that produces a standard A, the pitch against which musicians standardize their instruments, can be shown to have a frequency of 440 per second. To calculate the actual wavelength of a sound of a certain pitch, one can make use of equation 11-1. This tells us that the frequency, represented by the Greek letter nu, is equal to the velocity of the wave, represented by the lowercase letter v, divided by the wavelength, represented by the Greek letter lambda. Solving for equation 11-1 for lambda, we find that lambda equals velocity divided by frequency. Equation 12-1. The piece of information we need to make equation 12-1 useful is the velocity of sound. This velocity may be determined with considerable accuracy by a straightforward experiment, which was first carried through successfully in the early 17th century. Suppose a cannon is set up on one hill, and observers are stationed on another hill, a known distance away. When the cannon is fired, the flash is seen at once, assuming that light travels so quickly that its journey from one hill to the other takes up virtually zero time, which is correct. The sound of the cannon, however, is heard only after a measurable interval of time. The distance between cannon and observers divided by the number of seconds of lag in hearing the cannon, the possession of a good timepiece is assumed, will give the velocity of sound. To be sure, if there is a wind, the compression waves will be hastened onward by the overall movement of the air, or slowed down, depending on the direction of the wind. What can be done, therefore, is to place cannon on both hills and fire each first one, then the other. Whatever effect the wind has in one direction, it has a precisely opposite effect in the other, and averaging the two velocities obtained will give the velocity in quiet air. The concurrently accepted velocity of sound at ordinary temperatures, say 20 degrees Celsius, or what is equivalent, 68 degrees Fahrenheit, is 344 meters per second, or 1,130 feet per second, or 758 miles per hour. This velocity varies a bit with temperature. On a cold winter day, it may be as low as 330 meters per second. On a hot summer day, as high as 355 meters per second. The temperature difference has important effects. During the day, upper levels of the atmosphere are generally cooler than air at ground level. As the upper part of a beam of sound waves penetrates the cooler strata, it slows up. The effect of that is to veer the entire beam upward. If you are walking and someone seizes your left arm, slowing that part of your body, you automatically veer leftward. At night, the situation is reversed, for the upper levels are warmer than the lower levels. The upper part of a beam of sound waves will quicken, and the whole beam will veer downward. It is for this reason that sound can usually be heard more clearly and over greater distances by night than by day. However, if we confine ourselves to room temperature, we may write equation 12-1 as lambda equals 344 divided by nu. Equation 12-2. Until recent times, sound traveled at a velocity much greater than that of any man-made vehicle, so for practical purposes, the velocity of sound did not concern the traveler. With the invention of the airplane, however, and with the steady increase in the velocities of which it was capable, the velocity of sound became of importance for reasons other than those involving the speed of communication. It is the speed of the natural rebound of molecules after compression that dictates the rate at which a compressed area restores itself to normal and compresses the next area. So it is this speed of rebound that determines the velocity of sound. It is also the speed of the natural rebound of molecules after striking a speeding plane that makes it possible for air to get out of the way of the plane. As the plane approaches the velocity of sound, then it approaches the velocity with which the air molecules can rebound. The plane begins to chase after the rebounding air molecules and, with increasing speed, more and more nearly catches them. Such a plane compresses the air ahead permanently, or at least for as long as it maintains its speed, since the air cannot get out of its way. This volume of compressed air ahead of the plane puts great strain upon the plane's structure. For a time, in 1940s, it was felt that a plane would disintegrate if it approached the speed of sound too closely. Thus, talk began to be heard of a sound barrier, as though the velocity of sound represented a wall the plane could not break through. The ratio of the velocity of an object to the velocity of sound in the medium in which the object is traveling is called the Mach number, in honor of the Austrian physicist Ernest Mach, 1838 to 1916, who toward the end of the 19th century first investigated the theoretical consequence of motion at such velocities. To equal the velocity of sound is to be moving at Mach 1. To double it is to be at Mach 2, and so on. A Mach number does not represent a definite velocity, but depends upon the nature, temperature, and density of the fluid through which the object is traveling. For normal air at room temperature, Mach 1 is 344 meters per second, or 758 miles per hour. Improved design of planes enabled them to withstand the stresses at high velocities, And on October 14, 1947, a manned plane broke the sound barrier by traveling at a velocity of more than Mach 1. Since then, velocities of Mach 3 and more have been attained. An astronaut circling the Earth at a speed of 5 miles per second might be said to be traveling at Mach 25, if the velocity of sound in ordinary air is used as a comparison. However, the astronaut is traveling through a near vacuum across which no significant amount of sound is conducted, and Mach numbers do not really apply to him. A plane traveling at supersonic velocities greater than Mach 1, carries its sound waves ahead of it, so to speak, since it travels more quickly than they could alone. The volumes of compression are brought together, and instead of a smooth progression from compression to rarefaction and back, as in ordinary sound waves, there is a sharp dividing line between a volume of strong compressions and the normal surrounding atmosphere. The strong compression streams backward in a cone-shaped band, with an angle depending on the Mach number, and is called a shock wave. A similar shock wave streams back from speeding bullets too. It is also formed by the effect of lightning bolts, for instance, which will energetically expand air at velocities greater than Mach 1. The shock wave is an example of a wave form that is not periodic. If a plane traveling at supersonic velocities slows down or veers off, the shock wave will revert to ordinary sound waves, carrying volumes of unusually strong compression and rarefaction, however. In this train, sound waves expand and weaken as they travel, but if they are fairly close to the ground to begin with and happen to be directed downward, they will strike the ground with considerable strength, producing the now well-known sonic boom. Thunder is the sonic boom produced by lightning, and the crack of a bullwhip is a miniature sonic boom, since it has been established that the tip of such a whip can be made to travel at supersonic velocities. The velocity of sound, when spoken of simply as such, always implies its velocity through air. However, sound travels through any material body, and its velocity varies with the nature of the body. Intermolecular forces in liquids and solids, stronger than in gases, bring about a much quicker rebound after compression. Consequently, sound travels with greater velocities through liquids and solids than through any gas, and the more rigid the substance, and hence the stronger the intermolecular forces, the greater the velocity of sound through it. In water, sound travels at a velocity of 1,450 meters per second, or 3,240 miles per hour, and in steel it travels at a velocity of about 5,000 meters per second, or 11,200 miles per hour. The musical scale. Sounds of different pitch can be produced in musical instruments by striking or plucking strings of different length and thickness, as in the piano or harp, by using few strings, but altering their effective length, by pinning one end with the finger at varying points, as in the case of the violin, by allowing sound waves to fill tubes which may be lengthened or shortened by physical movement, as in the trombone, or by blocking or unblocking certain sections of the tube by stopping a hole with a finger, as in a flute, or depressing a key, as in a trumpet. When two notes are sounded, either together or one after the other, the combination is sometimes pleasant and sometimes unpleasant. This is partly a subjective and cultural matter, for we like what we are used to, and many types of music, such as rock and roll or traditional Japanese, sound unpleasant to the uninitiated, but very pleasant to the devotee. Nevertheless, if we confine ourselves to the serious music of the West, we can come to certain conclusions about this. When two notes are sounded together, the result is not two separate trains of sound waves, each traveling independently through the air. Instead, the two waves add to each other to form a resultant wave. To make things very simple, suppose that two sound waves are each of the same frequency but are sounded in such a way that one is half a wavelength behind the other. Whenever one sound wave is forming in an area of compression at one point, the other is forming an area of rarefaction there. and vice versa. The two effects cancel each other and the air does not move. As a result, the two sounds taken together produce silence. And this phenomena is called interference. It is difficult to picture this if we think of longitudinal waves. However, if the longitudinal waves are pictured as analogous transverse waves, as they invariably are for this purpose, interference is easily pictured. Wherever the sine curve of one sound wave goes up, the sine curve of the other goes down. And if the two are added together, a horizontal line, no wave at all is the result. On the other hand, if two waves of the same frequency are sounded exactly in phase, they would add to each other, so compressed areas are more compressed and rarefied areas are more rarefied than if either sound had been produced alone. In transverse wave analogy, the crests and troughs of the separate waves would match, and the resulting crests would be higher and troughs deeper of the two waves together than of either alone. The ear would hear one sound of the proper pitch, but louder. This is reinforcement. Actually, perfect interference or reinforcement is unlikely. Instead, two or more waves will combine, reinforcing here, interfering there, and will form resulting patterns of very complicated form that will not at all resemble the regular sine waves of individual notes. However complicated these patterns may be, they will remain periodic. That is, a small unit section of the pattern can be taken, and the entire pattern can be shown to be made up of a succession of these units. In 1807, the French physicist Jean-Baptiste Joseph Fourier, 1768 to 1830, studying waveforms, generally showed that any periodic wave pattern, however complicated it might seem, could be separated by appropriate mathematical techniques into the individual sine waves making it up. The mathematics involved is referred to as harmonic analysis because it can be applied to musical sounds. The wave patterns of musical sounds are composed of separate sine waves that display an orderly set of interrelationships. Where this is not true, but where the component sine waves are chosen and combined at random, so to speak, the result is not music, but noise. The difference is analogous to that between an orderly but complicated geometric figure and the same lines combined in random fashion to produce a scribble. Fourier's methods could be used to analyze the wave pattern of noise too, so perhaps it should be referred to by the more neutral term wave analysis. Restricting ourselves to very simple cases, and without inserting appreciable mathematics, let's consider two notes of different pitch, and therefore of different frequency, sounded together. The compressed regions of the sound wave, or the crests if we wish to speak in the more easily visualized transverse wave analogy, would be coming at shorter intervals in the case of the note of higher frequency, and they would overtake those of the sound wave with the lower frequency. Suppose one note has a frequency of 250 per second and another note of 251 per second, and suppose they start in phase. The first crest for both appears simultaneously. The second crest of the 251st second note appears just a little sooner than the second crest of the 250-second note. The third crest appears still sooner, and the fourth crest appears still sooner. At the end of 1 second, however, one note has completed exactly 250 vibrations, and the other exactly 251 vibrations. They are back in phase, but the 251 second note has gained one complete crest. Each succeeding second, the 251 second note gains another complete crest. At the point where the two notes are in phase, crest for crest, there is a short period of complete reinforcement, and the note sounds loudly. As the second progresses and the crests fall more and more out of phase, there is more and more interference and the sound becomes softer. At the half-minute mark, midway between two in-phase periods, the notes are completely out of phase, and the crests of one match the troughs of another, and there is a short period of complete interference. The result is a regular swelling and dying of sound, with the maximum loudness coming at second intervals when the crests match. Such periodically changing loudness, when two notes are sounded together, is called a beat. Suppose the two notes had frequencies of 250 second and 252 second respectively. Then after half a second, one vibration would have completed 125 vibrations and the other 126 vibrations. And they would be back in phase with crest matching crest. This would be repeated every half second, and there would be 2 beats per second. The number of beats per second, where two notes are sounded simultaneously, is generally equal to the difference in the frequencies of those notes. If beats are infrequent enough to be heard separately, they render the sound combinations unpleasant to the ear. Apparently, 30 beats per second is maximally unpleasant. Where beats are more than 60 per second, however, they melt into each other as far as the ear is concerned, and the combination of sounds seems pleasant or harmonious. Consider two notes, of which one has a frequency exactly double the other. One has a frequency of 220 seconds, let us say, and the other 440 seconds. The ratio of frequency is 1 to 2. The number of beats when the notes are sounded together is 440 to 220, or 220 a second. The beats duplicate the lower note, so the two notes seem to melt into each other and be almost the same note. They go well together. It was Pythagoras who first noticed that notes that go well together are related by these small whole number ratios. He had no method of measuring frequency itself, but he considered strings of different lengths. He found that two strings with lengths in a 1 to 2 ratio produced a pleasant combination. So did strings with a 2 to 3 ratio and a 3 to 4 ratio. Pythagoras wandered off in mystical fashion from these sound observations, sound in both senses. He assumed that the interplay of small whole numbers in the production of pleasing sounds fit in with his views that all the universe was ruled by number. He and his pupils speculated that the planets themselves produced sounds, the so-called music of the spheres, with notes based on their relative distances from the Earth. Science did not free itself from these notions for 2,000 years. Suppose, then, that we start with a note of 440 per second frequency, the standard frequency for musicians, and call it A. A note of twice the frequency sounds so much like it that we can call that A too, and we can use the letter for a sound of half the frequency, for that matter. In fact, we can have a whole series of such A's with frequencies of 110 per second, 220 per second, 440 per second, 880 per second, 1760 per second, and so on, extending the range, if we chose, both upward and downward indefinitely. Between any two successive A's, we can introduce other notes with frequencies that bear some orderly arithmetical relationship to the A notes and to each other. It is customary to introduce 6 other notes in the interval. These are lettered B, C, D, E, F, and G. Thus we have from A to A the notes A, B, C, D, E, F, G, A. In passing from A to A, there are 8 notes, counting both A's, and 7 intervals between notes. The span from A to A is therefore called an octave, from a Latin word for eighth. Other spans are spoken of in plain English. The span from C to G, C, D, E, F, G, involving as it does 5 notes, is a fifth, while the span from C to F is a fourth. The frequencies associated with the notes from 220 per second A to 880 per second A are as follows. A equals 220, B equals 247.5, C equals 264, D equals 297, E equals 330, F equals 352, G equals 396, A equals 440, B equals 495. C equals 528. D equals 594. E equals 660. F equals 704. G equals 792. And A equals 880. The range from 220 per second to 440 per second is 1 octave, and that from 440 per second to 880 per second is another octave. Each note in the upper octave is double the corresponding note in the lower octave, so the interval from B to B is an octave. So is the interval from C to C, from D to D, and so on. Remembering to double the frequency for each higher octave and halve it for each lower octave, you can write the frequencies for any note in any octave. If the successive notes within any octave are sounded, they sound just like the corresponding notes within any corresponding octave, lower or higher. The standard piano keyboard covers a range of a little over 7 octaves. If the white notes are sounded, one after the other, one can easily detect the same tune to be repeated 7 times at successively higher pitches. The frequencies are interrelated by ratios that can be expressed in small whole numbers. The ratio of G to C, for instance, is 396 by 264, or 3 to 2. The ratio of F to C is 352 to 264, or 4 to 3. It is these simple ratios that Pythagoras studied, and it is the simplicity of the ratios that sets up beats that reinforce the notes themselves and make them blend well together. That is why fifths and fourths are much used as intervals between successive notes. Then, too, the ratios of C, E, and G are 264 by 330 by 396, or 4 by 5 by 6. And the 3 notes sounded together as a major triad make a pleasing sound combination, or chord. F, A, and C also make a major triad, and so do G, B, and D. In fact, the note intervals are so designed that every note can be part of one or another of these 3 major triads. If the ratio of the frequency of adjacent notes is considered, it turns out that B to A as 9 to 8. The ratio for D to C and for G to F is also 9 to 8. The ratio for E to D and A to G is not quite that, but it is close, 10 to 9. In other words, of the 7 intervals between the notes of the octaves, 5 are roughly equal size, and we call them whole intervals. The frequency ratio of F to E, however, is only half as large, for it is 352 to 330, or 16 to 15. This is also true of the ratio of C to B. This may be easier to see if we express it another way. A ratio of 9 to 8 represents an increase in frequency of 12.5%, and one of 10 to 9 represents an increase of 11.1%. The ratio 16 to 15, however, represents an increase of only 6.7%. In passing from B to C, or from E to F, then, we are traversing only half an interval. If we start from A and go up the notes through B, C, and so on, we will be passing intervals in the following pattern: whole, half, whole, whole, half, whole, 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 half, whole, whole, half, and so on. Successive half intervals are separated by 2 whole intervals, 3 whole intervals, 2 whole intervals, 3 whole intervals, and so on. When we sing the scale using the traditional names for the notes, do, re, mi, fa, sol, la, ti, do, through long habit, we insist on placing the half-note intervals between mi and fa, and between ti and do. Any other arrangement sounds wrong to us. We therefore want the 7 intervals of the octave to fall into the following pattern: whole, whole, half, whole, 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 half. If you check back, you will see that this particular arrangement can only be brought about if we start with do on the C note. It doesn't matter which C. Then re becomes D, mi becomes E, fa becomes F, Sol becomes G, La becomes A, Ti becomes B, and Do is C again. The Mi-Fa half interval corresponds to the E-F half interval, and the Ti-Do half interval corresponds to the B-C half note interval. The arrangement of notes you sound in singing the scale now matches the successive notes you tap out, beginning at C on the white keys of the piano. If you start on any white key of the piano other than C and play the successive white keys, the piano and you will sound half intervals at different points in the scale, and the piano, not you of course, will sound dreadful. It is desirable to be able to play the scale from any point on the piano keyboard, so that the range of the scale can be adjusted to a particular human voice, for instance. For this reason, in every octave, 5 black notes are inserted to break up the 5 whole intervals. This accounts for the familiar black note pattern of 2 C, D, D, E, and 3 F, G, G, A, B, all along the keyboard. Now, the scale can be sounded by beginning at any note on the piano, either white or black, provided you remember to choose your notes carefully and play sometimes black and sometimes white. Only if you start on C, however, can you play the scale by sounding successive white notes only. It is for this reason that C seems a natural Do, and that the key of C is the simplest key to play for beginners. White keys only, for the most part. Middle C is the particular C that is about at the midpoint of the piano keyboard, and it is the C with the frequency 264 per second. Modification of pitch. Pitch will change if the source of sound is moving relative to the hearer. Suppose a distant train, standing motionless, sounds a whistle that has a frequency of 344 per second. In that case, when the sound wave reaches us, 344 compression rarefaction combinations will strike our eardrum each second. Since sound at room temperature travels at 344 meters per second, successive areas of compression are a meter apart. Suppose next that the train is moving rapidly toward us at a rate of 34.4 meters per second, 75.8 miles per hour, or just 1/10 the velocity of sound. It is still sounding its whistle. One region of compression is moving ahead of it, and by the time it has moved a meter, another region of compression is emitted. By that time, however, the train has moved forward 1/10 of a meter, and the second region of compression is only 0.9 meters behind the first. This happens for all successive regions of compression if the train maintains a steady pace. For this reason, sound waves from the whistle of the approaching train enter our eardrum 0.9 meters apart, and in 1 second, 344 by 0.9, or 382 of them, strike the eardrums. A person on the train, and therefore moving right along with the whistle, receives 344 regions of compression in 1 second. The ratio 382 to 344 is close to 9:8. So the sound is a whole interval shriller. See page 172, for the person watching the train approaching than for the person on the train. On the other hand, if the train were receding, then by the time a region of compression had moved a meter toward the hearer and a new region of compression was due, the train would have moved 1/10 of a meter away, and the two areas of compression would be 1.1 meters apart. The frequency would be 344 to 1.1, or 312 per second. Now it is deeper by nearly a whole interval than it would sound to the person on the train. If the train passed us at this velocity, the sound we heard would shift suddenly from a frequency of 382 per second as it was approaching and passed to 312 per second as it passed and receded. This phenomena is called the Doppler effect, in honor of the Austrian physicist Christian Johann Doppler, 1803 to 1853, who first studied the effect and explained it correctly in 1842. Pitch can be made to vary in a much more subtle way, too. The same note sounded with the same loudness on the piano, violin, and clarinet sounds different to us. We can tell which instrument is sounding the note. This difference in notes that are identical in pitch and loudness is a difference in quality or timbre. To explain this, we must consider that the vibrations of a string or of any sound-producing device are actually more complicated than I have described them to be. A string, for instance, may indeed vibrate all in one piece to produce a vibration and therefore a sound wave of a given frequency. In the transverse wave analogy, this would be a simple regular sine curve and is the fundamental note. It is the fundamental note we usually think of when we speak of the frequency of a particular note. However, the string may also vibrate as two halves, one half moving to the right and the other half moving to the left, and vice versa. The midpoint of the string, bounding the two halves, serving as a motionless node. Each half of the string vibrates at twice the frequency of the whole string, so a note is sounded with just twice the frequency of the fundamental note. The string may also vibrate in thirds, in fourths, in fifths, and so on, to produce notes with frequencies 3 times, 4 times, 5 times, and so on, that of the fundamental notes. All these notes of higher frequencies are called overtones. The fundamental note and the various overtones are sounding simultaneously. The actual motion of the string is a combination of all. The fundamental note remains dominant, but the overtones add their waveforms, and therefore the resulting waveform is far more complicated than a simple sine curve. Furthermore, for strings under different conditions, to say nothing of other sound-producing devices, the overtones may be receiving different proportionate stress. Certain overtones may be stronger in some cases than in others, so the final difference imposed on the eardrum is great enough for us to detect. This difference can be magnified by methods of selecting some overtones from the rest for special magnifications. Let's see how. A vibrating object may force another to vibrate in unison, so the second object sets up the same sound wave pattern and produces the same sound. If a vibrating tuning fork has its stem placed in contact with a table, its sound is suddenly louder because now the entire table is vibrating in unison. Such a forced vibration need not even be the result of direct physical contact between solids. Indirect contact through air may be sufficient. A given vibration will set the air pulsing in longitudinal waves. These waves will in turn set the eardrum vibrating in unison. The eardrum will move inward when a region of compression strikes and outward when a region of rarefaction does. It moves a greater distance from the equilibrium position as the regions become more compressed and more rarefied. It is through such forced vibrations that the eardrum exactly duplicates the original vibration, and we are able to judge, via a complicated hearing mechanism we will not describe here, the pitch, loudness, and even the timbre of a sound. There are occasions, however, when one particular frequency is more easily forced than another on a second body. Imagine yourself pushing a child on a swing, for instance. The child on a swing represents a form of a pendulum and has a natural period of vibration. If you apply successive pushes to the swing at random intervals, you will often push the swing as it is moving back toward you, and will cancel what motion it possesses, slowing it. By persisting, you will keep the swing moving in accordance with your pushes, but you will expend a lot of energy doing so. If, however, you timed your pushes to match the natural period of vibration of the swing, you would push each time as the swing begins to move away from you, thus adding to its velocity and increasing it further with each swing and rhythmic push. At the expense of far less energy, you would get a far more rapid and extended swing. Marching soldiers crossing a bridge are supposed to break step Otherwise, if the thud of the footsteps in unison happened to match the natural period of vibration of the bridge would swing in wider and wider arcs until it finally broke apart. The situation is analogous for sound waves. The sound wave of a particular note would push another object with each region of compression and pull it with each region of rarefaction. If the rhythmic push and pull did not match the natural period of the receiving object, the forced vibration could only be obtained at the natural expense of considerable energy being used to overcome that natural period. If, however, the frequency of the note just matched the natural period of vibration on the receiving object, the latter would begin to vibrate more and more. This is called resonance, from Latin words meaning to sound again. Any given sound wave would produce far more vibration in a resonating object than in any other kind. In fact, only the resonating object might produce sound waves strong enough to be audible. Suppose, for instance, you raise the top of a piano to expose the wires and step on the loud pedal to allow all those wires to vibrate freely. Now sing a short, loud note. Only those wires that vibrate at the frequency of that note will resonate, and when you stop singing, you will hear the piano answer back softly in the same note. Musical instruments depend upon the resonance of the materials making up their structure to strengthen and add richness to the notes produced. Pianos have a sounding board just under the wires, and this device can resonate with the various notes. Without that board, the notes sounded by the wires would be quite weak. Naturally, the resonating portions of each instrument, although resonating to almost all the notes, the resonating portions are complicated in shape and different parts have different natural periods of vibration, do not do so with equal efficiency. The wood of a violin resonates to the notes produced by it, but it may resonate more efficiently to some overtones than to others. No two violins are of exactly the same shape, or of exactly the same wood, with the same grain arrangement, or possess exactly the same varnish. As a result, there are subtle differences in resonance from instrument to instrument. The Italian violin maker Antonius Stradivarius, 1644 to 1737, manufactured violins that are the despair of imitators, for it is almost impossible to duplicate their richness of tone. The sounds we ourselves make produce resonances in the air filling the hollows in throats, mouths, and nasal cavities. The natural vibrations of the air depend on the shape and size of the cavities, and since in no two individuals are these cavities of precisely the same shape and size, voices differ in quality. We usually have no trouble recognizing the voice of a friend from among a large number of others. Reflection of sound. A ripple in a water tank is turned back on itself when it strikes the rim of the tank, having progressed, let us say, leftward prior to contact. It proceeds rightward thereafter, much as a billiard ball does that has struck the edge of a pool table head-on. The water wave has been reflected, from Latin words meaning to bend back. Sound waves can be reflected too. A mountain wall will reflect them, for instance. A word shouted across a valley is heard almost at once as it leaves the lips, being conducted through the air from lips to ear. It is then heard again seconds later, after the sound wave has reached the mountain wall, been reflected, and crossed the valley a second time. This is the echo. If mountainsides are properly arranged, more than one echo may be heard. Similar echoes may be heard in tunnels, in large empty rooms, and indeed anywhere where hard surfaces reflect sound rather than absorb it. In ellipsoidal rooms, a sound uttered at one focus of the ellipse will spread out in all directions. However, in reflecting from various portions of the wall and ceiling, it will concentrate upon the other focus. Two people standing at the foci can converse in whispers, even though separated by a large distance. Such whispering galleries always amaze those who have never encountered one before. In rooms of moderate size, the length of time taken for a sound wave to travel to a wall, be reflected to an opposite wall, be reflected once again to the first wall, and so on, is so short that distinct echoes will not be heard. Instead, a series of very rapid echoes will blend into a dull, hollow rumble that may persist audibly for a considerable time after the original sound is no longer being formed. This persistence of sound is called reverberation. The study of the behavior of sound in enclosed places, particularly with regard to such reverberation, is called acoustics, from a Greek word meaning to hear, a term that is sometimes applied to the study of sound generally. Reverberation can represent a great inconvenience. A lecturer may find that his words cannot be heard because of the dying sound of his previous words. An orchestra may find its best efforts reduced to discord as previous notes live on past the time when they are wanted or needed. Reverberation can be reduced by draping the walls, using a soft, pulpy material for the ceiling, or even by the presence of an audience in winter clothing. When sound waves enter the small interstices of fabric or other porous material, contact of the moving air molecules with solid material is made over a hugely increased area. Friction is increased, and sound energy is converted into heat. The sound waves, in other words, are absorbed rather than reflected. This can be overdone. If reverberation is reduced to too low a level, there seems a deadness to sounds. A reverberation period of 1 second, or even 2, if the room is very large, is aimed for. Sound waves are not always either reflected or absorbed, nor are water waves. There is a third alternative. Sound waves, and water waves too, can bend around obstacles and continue onward. It is because of this that we have no difficulty hearing someone call from behind a tree or from around a corner. This ability to bend around obstacles is not the same for all kinds of waves. In 1818, the French physicist Augustin Jean Fresnel, 1788 to 1827, was able to show, in connection with his studies of wave motions generally, that whether a wave was reflected or not depended upon the comparative size of the wavelength and the obstacles. When an obstacle was the size of the wavelength or less, it did not reflect the wave, which instead bent around the obstacle. If the obstacle was considerably larger than the wave was reflected. Consider the common sounds we hear about us every day, with frequencies, let us say, through the middle range of the piano, from C, below low C, to C above high C, a range of 4 octaves. The range of frequencies extends from 66 per second to 1056 per second. If we make use of equation 12-1, we see that the range of wavelengths over these 4 octaves is from 5.2 meters down to 0.32 meters, roughly from 1 to 18 feet in common units. The common obstacles we meet with fall within this range of size and do not reflect such sound to any great degree. So sound bends. This bending is, of course, more likely for the deeper sounds than for the shriller ones. We judge the direction of a sound by the inequality of loudness in the 2 ears, automatically turning our head until both ears hear the sound with equal loudness. Our head is large enough to reflect somewhat a shrill sound coming from one side. There is then a considerable reduction in the intensity of that sound making its way around our head to the other ear. We have no trouble, therefore, locating a child by its shrill cry. On the other hand, the deep tones of the lower register of an organ move around our head with ease and sound equally intense in both ears. The sound seems to come from all around us. This in itself lends majesty to the swell of the organ. The full range of the piano covers 7.5 octaves. The lowest note possesses a frequency of 27.5 per second. and a wavelength of 12.5 meters. We can hear still deeper sounds. However, the usual extreme in that direction is 15 per second, a sound with a wavelength of 22 meters. The highest note of the piano possesses a frequency of 4,224 per second and a wavelength of 0.081 meters, or 8.1 centimeters. The adult human ear can hear sounds with a frequency as high as 15,000 per second, wavelength 2.2 centimeters, and the child can sometimes hear a frequency as high as 20,000 per second, wavelength 1.7 centimeters. Such extreme shrill sounds will be reflected quite well by objects too small to reflect sounds in the more common range. The high-pitched creak of a cricket may be reflected so well by various objects that it is next to impossible to tell exactly where the original sound is coming from. It is of course possible for objects to vibrate with frequencies of less than 15 per second and more than 20,000 per second. When this happens, sound waves are produced which are not audible. Those that are too deep to be audible are infrasonic waves, from Latin words meaning below sound, while those that are too shrill to be audible are ultrasonic waves, from Latin words meaning beyond sound. Infrasonic waves are comparatively unimportant, except where they become energetic enough to do physical damage, as in earthquakes. Ultrasonic waves impinge upon us more often and in many ways. For one thing, they are not inaudible to all forms of life. Many animals smaller than ourselves can both produce and hear them. The silent whistles to which dogs respond produce ultrasonic waves that they can hear, though we cannot. The singing canary produces ultrasonic waves that would undoubtedly greatly add to the beauty of the song if we could but hear them. The squeaking mouse also produces them, and the waiting cat can hear them where we cannot, which increases the efficiency of the feline stalk. Ultrasonic sound waves, with wavelengths even shorter than those of the shrillest sounds we can hear, can be reflected efficiently by quite small objects. Bats take advantage of this fact. They emit a continuous series of ultrasonic squeaks while flying. These have frequencies from 40,000 to 80,000 per second, and therefore have wavelengths from 8 to 4 millimeters. A twig or an insect will tend to reflect such short wavelengths, and the bat, whose squeaks are of extremely short duration, will catch the faint echo between squeaks, and can thus guide its flight by hearing alone, and continue flying with perfect efficiency, even if blinded. This process is called echolocation. Men duplicate this effect by making use of beams of ultrasonic waves underwater. These are reflected from objects such as the sea bottom, jutting rocks above the sea bottom itself, schools of fish, or submarines. The technique is referred to as sonar, an abbreviated form of sound navigation and ranging, where ranging means getting the range of an object, that is, determining its distance.